All right, good afternoon, everyone. We have our Jones Seminar speaker today, who is Professor Bas Almassalkhi, who is the L. Richard Fisher Associate Professor at the University of Vermont. His research focuses on engineering flexibility for power and energy to optimize grid utilization, and interest spans advanced distribution, transmission system operations, modeling, control, optimization of distributed energy resources, or DERs, for grid-aware coordination and all things battery storage. He has won a number of awards. He's the founding director of UVM's newest Center on Energy and Autonomy. His work has featured in IEEE Spectrum. He has won the Edison Career Award. He also, among other things, he also has been a co-founder of a company called Packetized Energy, which is a clean tech startup that was acquired by Energy Hub in 2022. He has his training from Michigan, where he got a PhD in electrical engineering systems, and a dual major undergrad in electrical engineering and applied math from University of Cincinnati, Ohio. So with that, please join me in welcoming Professor Almassalkhi.
Thank you, everyone, for attending a Friday afternoon seminar. I can imagine the week has been pretty long, the month has been long, the year has been long. And so I appreciate your time. And thank you, Amos, for perfect handling of my disorganization. And so I don't think I've ever been this on time. And so I appreciate your effort. And thank you, Vikrant, for the invitation. So this talk is basically two pieces. One, I'll talk a little bit about high-level background. It'll go pretty fast. The 20 slides or so will go really fast. Then we'll kind of slow down and land on some of the technical challenges that I see as kind of impediments to making electrification scale in the next 5 to 10 years. So I am at the University of Vermont. I think a couple of you today told me that they didn't know there were people working on power and energy in Vermont. And so a good reason and good motivation to kind of share a little bit about what is happening at Vermont. And so, in my opinion, it's one of the best places in the country to work on power and energy. It's also a beautiful place to be. We have lots of labs, lots of offices. And in academia, we talk a lot about resting on the shoulders of giants. And when it comes to energy, Vermont is a place of a lot of giants. They might be small, but they're mighty. And so you can see, first efficiency utility selling megawatts. First 100% renewable utility. I think Green Mountain Power continuously win fast companies, most innovative energy companies in the world, competing with Apple, Google, Tesla. This is a utility. And so then we have Vermont Electric Co-op, which has 200 megawatts of generation, but only 50 megawatts of load. That makes it really interesting to be a utility. And like any good faculty, we should start with a pop quiz. And so this is 2 different days in April 2024. The overcast day in gray and the sunny day in yellow. Can someone tell me what's going on? What's happening? You just shout out anything, right? The faster you answer, the more wrong you can be. Duck curves are nice. What makes the duck curve? Yeah. Yeah. So there's about, 500 megawatts of solar? That's pretty crazy. All right, what else? What happens in the middle of the day? What happens to that duck? This is real data. This is all of Vermont. Is someone speaking on the internet? Oh, yes. Hey, Kang.
Why this is not a smooth duck curve? I mean, there's a bump in the middle from 2 to...
Yes. You have to provide answers, not questions. Solar eclipse. Bingo. But what else is happening? What are the other 2 pieces? I'll speed things up a little bit. 30 megawatts of distributed batteries being dispatched during you see the hill that gets clipped off? That's 30 megawatts of distributed batteries. You see the spikes at the end of the day? That's 10 megawatts of controlled electric water heaters. And so you have a beautiful example of nature and nurture, which is at the heart of any liberal arts education. At Vermont, we don't just have amazing data, we don't just have awesome utilities at the forefront of kind of the energy innovation cycles. We also have amazing partners that we work with in various formats. So we have the federal side, and we have industry and national labs. And so over the last 10 years that 11 years that I've been at UVM, we've been able to build critical mass. And so today at UVM, we have 40 PhD students, 15 faculty, and 7 different graduate programs involved in energy and autonomy. It's pretty awesome. Specifically, if you zoom in and say who's working on power and energy systems, we have 27 full-time researchers, 19 graduate students, 4 senior researchers, and 4 tenure-track faculty. And so this is something that I'm super proud of to be able to grow over the last 10 years. And it's something that's really taken off in the last 3 years alone. So I could show you a picture of 4 years ago when it was me and 2 students. And so it's been a really exciting experience, and we had to rethink a lot of ways in which we grow groups that recruit and retain students. And so within my own group, I work very closely with 3 senior researchers in black boxes. I co-advise the folks in green, and everyone else I meet with basically all the time, at least once a week. And so it's a really awesome group. Everyone is kind of working on different things, obviously. And it's just, I'm very happy with the group we have. And so every one of our students kind of work on problems that are relevant to various forms of energy technology, energy innovation. And one of the recent examples of kind of the ability to translate that research that we do in our labs outside of the classroom, outside of the academic walls, is packetized energy, which we launched in 2016, which was acquired in 2022 by Energy Hub. And being able to see kind of academic papers and patents developed since 2012, 13, 14, kind of achieve access to scale has been really awesome. And so students working in our lab, it's very motivating to see papers and research actually make it into the real world. And so that has been a really awesome experience. And this is a company I co-founded with Paul, Jeff, and myself. And so the ethos is kind of our group is, if it works, will it matter? And that drives a lot of the research questions we pursue when we work with students and other partners. And so I can give you a quick highlight of some of the interesting topics that I find in my group. I think there are a number of students attached to each of them, but grid control architectures I'll talk about today. I think there's a lot of interest in dynamics and resilience, right? You can ask Spain and Portugal. Hybrid energy systems, I think, is another avenue for, there's room for innovation in how PV batteries and controllable loads should interact with each other. There's a lot of interest in turning data into meaningful models, and then thinking about these big networks we have are fairly complicated. Power systems are suffused with complex networks. Are there ways in which we can represent these networks in reduced manners that are still accurate and meaningful? And then we do a lot of distributed control and optimization, whether that's smart EV charging, not from 1997, but 2017 on, or it could be water heater controls, or it could be battery dispatch. And so we work on a lot of different interesting problems that I'm happy to talk about at any other time. The other thing I've started to do is move from virtual power plants to physical power plants. And so at UVM, we were able to convince DOE to invest in hardware. And so we've been able to install a 14 kilowatt electrolyzer. We have batteries that can be dispatched. We have about 50 kVA of power supplies that we can activate. To do power electronics, we have some inverters that we can basically control and design algorithms for. And then we have a real-time grid simulator. So we can start to pull together some of these hardware pieces that we always envision in our models. We can also do a lot of model validation. And then we have awesome students as well. I think it's 3 weeks ago we passed electrical inspection, so that was a 2-year journey to build a hardware lab. And so now we have AC power supply, DC, we have inverters. It's a really fun place. Lots of questions to be answered. The other thing we're really interested in is working closely with our collaborators in industry. Vermont does not have a lot of money, but they have a lot of data, as we saw from the first slide. And so what we've been working with is really trying to turn these data sets into better models, and then turning those better models into more informed decisions. Because when it comes to electrification, when it comes to resilience, we need some kind of proof in the pudding. That if we claim that we can enhance resilience, can we show it on meaningful models? If we want to optimize utilization of networks or workforces, that's something we can start to integrate into these electric grid models that we are building and validating. And so we have lots of really awesome partners in Vermont on this. All right, quick overview. Electric grid 101. I assume you guys know, right? Power plants, step up the voltage to transmission, step down the voltage to distribution, and then we have consumers and demand. Right? Their power system has one flaw. Everything is a 4 or 5 letter acronym. Right? And so DSO, DSP, DO, and utility are kind of the same thing. Think of them like front of the meter. ISO, TSO, RTO, and BA, think of those as transmission systems. And so if you were to look at a textbook from 50 years ago, that's what it looked like. If you look at a textbook from 20 years ago, that's what it looked like. But things are changing now. Right? Solar panels are so cheap. I think it's the cheapest source of energy on the planet. Wind farms have been installed in various places. Carbon policies have been pushed. So state policy goals have been pushed. But there's more to come. Electric vehicles are making their way through to homes, right? Transformers were built in size based on the refrigerator rule. An EV is like 7 refrigerators. Smart thermostats, batteries are being deployed, right? If you have $6,000, you can drop it on a battery-equipped induction stove. Pretty cool, 120-volt outlet, another controllable device. And so what we're seeing is this rise of these virtual power plants, right? These DER operators that are managing all these cool behind-the-meter devices. You have the utilities, front of the meter, and then you have all kinds of market interfaces in the transmission. And so as an engineer, I look at the system, I can't tell if it's a system or it's chaos. And so I'll try to talk through how we can systematize some of these changes. And specifically, which signals do we need to send to whom? And what information do we need to convey? And who needs to control what? Right? Who is in charge of resilience? And so the future grid that we're marching towards pretty quickly is a pretty open question. If you ask Mary Powell, let sun run, she can scale fast, and utilities are in the business of no, no, no. But if she scales fast and utility doesn't run along with her, what happens to the grid and reliability and resilience? If you ask Google, this is through Tapestry, flexibility is going to become the defining characteristic of a future grid. If you talk to Canary Media, you can see that utilities are kind of competing with a bunch of DER operators and virtual power plant operators. And competition might not be the right approach, and I would argue that the technology that we are heading towards is not really well understood by either party. Fairly strong statement. I would justify it through discussion. The last thing we have to remember is that energy systems serve people, right? They don't serve devices, they serve people. And so affordability is key, right? Energy burden and energy limiting behaviors are real, and those trade-offs need to be studied and understood really well in rate making and other cases. So the future of the grid is complicated. And so the need for flexibility is being touted as kind of the next step. Flexibility will give us affordability and reliability according to New York's Grid of the Future vision. Right? Specifically, they call out DERs and virtual power plants to achieve clean energy goals at a manageable cost at the highest levels of reliability. Right? Affordability and reliability must come together, and there are arguments that flexibility can achieve this. So let's talk about flexibility. Right? Where does flexibility come from today? Where does it come from? Right? I haven't defined it yet. Someone should say, what is flexibility? Right? Today, physical power plants provide the vast majority of the flexibility that the grid needs to provide reliable supply and resilience. But going forward to 2030, 2035, 2040, we're going to need to double the amount of flexibility that the grid needs to supply. And that's in part because of renewable generation and demand patterns. Right? I think what's it called, data centers have been a big discussion recently. And so a simple question would be, what is the flexibility of a generator? Right? If they do 90% of the flexibility, what do we mean by that? And so I have been thinking about this question for a while, and I kind of see 3 core elements, or 3, I guess, salient features of flexibility. Power deviation. Are you able to change your power output, and by how much? For how long can you sustain that deviation? And how fast can you deliver the deviation? Right? So for a generator, the capacity, availability, and ramp rate are key. And so we've been thinking about how do we generalize the notion of flexibility across all kinds of devices. And so we've been thinking about these reach and hold set. And that's a little bit loaded. And so this is something that Mazen has been working on recently. And so a power plant has no energy constraint, right? They can provide power effectively all the time, and they can provide it up to their capacity. And so if you were to plot their reach and hold set, you can see that a power plant can basically provide full capacity, let's say a megawatt generator, and it can provide it at all times. So it's not 6 hours, it just continues upwards. So it just ran out of space. So a reach and hold set for a generator is basically everything in blue on the right-hand side up to the capacity. And it can provide it at all times forever, assuming natural gas exists. But generators are not going to provide the only source of flexibility in the future. We're also going to be looking at batteries and demand response, or specifically DERs. And so the future of flexibility is going to be significant composition of demand-side resources and batteries. Depending on who you ask and which country you're in, it's going to be like 30 to 50% of flexibility provided by small resources. And so inherent to this question is, how do you manage millions of devices? Right? There are thousands of generators on the system today. We need to do millions of devices. And so we need some cohesive method in which we discuss what is flexibility. And so let's ask the simple question, what's the flexibility of a battery? Right? Keeping the same salient features, power deviation, available duration, and responsiveness. Right? I'm going to drop responsiveness because that's a power electronics question, inverter question. We'll leave that out for now. But if you think of the reach and hold set, how much flexibility can I provide, megawatts, and for how long can I provide it, hours? So a 1 megawatt battery, a 1 megawatt hour battery, what's the reach and hold set? How long can I provide a megawatt? Charging, for example. An hour? Doesn't it depend on the state of charge? Right? So at 50% state of charge, the reach and hold set of a battery looks like this. Right? The generator is completely filled out from 0 to 1. Right? The generator can do everything, but the battery can only do this at 50%. And so we can start to say, hey, if I want to dispatch this battery, its flexibility is defined by these reach and hold sets. As the state of charge changes, the reach and hold set changes. And so that's a single battery. What if I have 1,000 HVAC systems, 5 kW each? Right? If I want to dispatch them, I can't set a power set point, but I can change the temperature set point by 2 degrees. Right? So if I increase the temperature set point of a HVAC system or a thermostat by 2 degrees, what kind of reach and hold set do I get? Right? 1,000 HVAC, not a single HVAC, 1,000 HVAC. So this is super complicated. Mazen is working on this. It's really, really awesome work. I'm just showing one picture of his results because it fits in the reach and hold set. So we can compute these reach and hold sets. The actual computation is super complicated. It's an NP hard. It's a very, very large optimization problem. It's not NP hard. It's a very large optimization problem because 1,000 HVAC systems create population models, and these population models can have very large number of states. And so to compute these reach and hold sets for HVAC systems is actually really, really hard. And so Mazen has developed some really cool ways in which you can find an inner approximation, a simplified version of this reach and hold set for 1,000 HVAC systems, and the reach and hold set looks something like this. But the reach and hold set is different on a cold day, on a cool day, and on a hot day. Right? So it depends on the ambient condition, just like the state of charge of a battery. And so we can start to play with these different reach and hold sets and bring them together to quantify flexibility. And so whenever someone tells you what flexibility is, at least I hope you remember these 3 things. Right? Deviation, duration, and responsiveness. So now how do we integrate all this flexibility into the grid? Right? Thermostats need to abide by comfort and convenience of their consumers. If you're charging an electric vehicle, you can't leave them stranded on a Friday afternoon. Actually, last night I was charging my car, it was almost out. And I plugged it in and I prayed and I went to bed. I woke up and it was fully charged. But you never know. And so human constraints, devices serve people, not the other way around. We also have to think about reliability. Right? If I implement a bunch of controllable resources, it's going to bump into grid limits. How do we manage those grid limits? Then there are business models, risk management. Managing thousands of millions of devices means you're going to be dealing with some kind of stochastic resources. How do you manage that? What's the business model for it? I think RPE had the Perform program a couple of years ago that tried to look at some of these risk and market models. And then one of the most important pieces, which I won't talk about, is cybersecurity and data privacy. Super hard problem. I don't know how to fix that problem. But what I do know is that whenever a company and a utility agrees that they are cyber secure, that's basically just a handshake. Right? There's no proof that you can be cyber secure, at least as far as I know. And at Packetize, we were very careful designing really good protocols for how our data and devices were being managed. And so if you think through all these smart devices, all this flexibility, interacting together, that's effectively intelligent electrification. Right? We take a bunch of resources, we put a little bit of smarts on them, we make them deliver flexibility as megawatts deviations over different time steps and at different rates. And so then we have this orchestration of DERs as virtual power plants, VPPs. And this is Jigar Shah's famous figure from the Department of Energy report on virtual power plants. And so this report is very nice overview of virtual power plants, but it leaves, I think, a key question unanswered. Right? How do we architect the virtual power plants necessary to orchestrate all these devices? Right? What are the signals? Right? That communication link up there is super simple. How do we think through that orchestration? And there are many, many options. And anyone working on control systems or distributed control systems knows that there are many ways to design signals to achieve certain types of flexibility from resources or certain actions. And the other thing we can't forget is policy. And so FERC Order 2222, when it came out, we were so excited. Right? It was like high fives. We were so excited. Finally, DERs had made it. Right? They have access to markets. Right? I think it was DER inclusive markets. But deep inside on page 228 of FERC Order 2222 is a little line that says DERs can be dispatched as long as they don't pose a risk to reliable and safe operation of the distribution system. That's a rule. Utilities have the right to block any DER actions if they deem somehow that it impacts their risks. So the obvious question becomes, how do you manage that risk? What are the signals that would allow me to clear a DER to deliver flexibility if the utility is the one in charge of clearing it? What signals do I need to send? How do we manage it? Do you manage it like whack-a-moles, right? So every single action gets sent up and you have to clear it. You manage it once and done, kind of like PV hosting capacity maps today. Does a feeder hit some saturation limits and we're done with DERs forever? And so what I'll talk about next is that pathway, right? How do we go through thinking about the interaction between DER operators as virtual power plants and distribution operators as utilities? And so today's VPP practice is effectively what you see on the right or left. And so what you see today is that effectively operators access wholesale markets. Remember, TSO is the wholesale markets. And the only interaction between distribution operators and DER operators is effectively demand response, right? Crushing peaks. That's the focus, right? DER operators are not generally aware of grid conditions in the distribution system. Because they're not at scale, so it's not a big deal. Going forward, according to FERC 2222, utilities have effectively the veto right on every DER dispatch. And so are we heading towards what's called the total DSO architecture, where the DER serve the utility, not wholesale markets? Is that the angle? Maybe utilities can use DERs to shape their demand curves to be more efficient in their market interactions, right? Maybe they can use it to defer transformer upgrades in their network, but no more aggregators hitting up the wholesale markets. Or is there some hybrid in between? Something like a grid-aware dispatch, where utilities share a little bit of information with the DER operators so the DER operators can manage DERs reliably with some kind of guarantees. And so we might end up here. I think we can end up here if we design the system the right way. And so we'll talk about those things. So grid-aware dispatch or network-aware dispatch is a pretty common term these days in some of these conferences. Hosting capacity, operating envelopes is something that would fit over here on the grid-aware side. So Australia is pretty well known for managing PV with operating envelopes. And so if I'm managing resources, I'm managing networks, how do I ensure that both the requirements are met? And this isn't just my cartoon, right? I made these cartoons. But it's not a cartoon, it's real. This is New York's vision. This is what it used to look like. You see the aggregator has wholesale access market. This is New York's vision for distribution system platform. I forget the DSP. It's another acronym. Right, that aggregator has full access to wholesale markets. And what's the version 2.0? This is being discussed right now. Aggregators have no access to wholesale markets. That's a pretty big difference. If that goes through, we're looking at total DSO. That's a pretty big difference. Can aggregators survive if they don't have access to wholesale markets? Maybe if they have cheap API access. Right? So can the DSP, can the utility do it all? And so the total DSO architecture was pretty extreme in 2016. Everyone thought that virtual power plants and DERs and aggregators would somehow autonomously manage the grid for us. Right? Enphase came out with their grid-forming inverters, and everyone thought this was it. Now our grids will be managed by these really cool electronics and algorithms. Right? And so no one really thought that the utility would take over control of everything, which may or may not happen today. And so recently we've been hearing from folks, this is like Paul Lafarge. So Maryland is currently considering the idea of distributed capacity procurement, which means that utilities, instead of buying a big generator, will go out and procure 10,000 batteries. And these 10,000 batteries will be deployed strategically to provide the same level of capacity, but serving the utility's purpose. Right? It has a lot of really nice benefits. Right? Utilities know about the infrastructure, can site them, can dispatch them. You can defer upgrades and you can count that cost explicitly, really beneficial. And can utilities deploy something really quickly at scale? Open question. Green Mountain Power has their zero outage initiative, which is batteries and undergrounding of wires. It's a very utility-centric approach as well. And New York's Grid of the Future vision is also fairly utility-centric. And so these these architectures that no one really thought about in 2016 are appearing more and more likely. And so for the rest of the talk, I'll talk a little bit about how we can manage DER aggregators, talk about how we integrate with utilities, and then we'll talk about this hybrid DSO architecture. And so 2016, we wrote a proposal that was funded by DOE. We didn't realize it was the total DSO model, but it actually was. And so DOE funded this work in 2016 and thought it was afterwards, didn't fund it again because they thought it was too far ahead of its time. And so we're pretty happy to have some really cool results on total DSO architectures. All right. How am I on time? Half an hour. So half an hour to go. All right. If you are a virtual power plant operator, you're an aggregator, a common approach to manage your resources is like a sprinkler. Right? You set a timer or you set a price. You turn all your devices on or you turn all your devices off. Super simple. It's very cheap to implement. This is like Duke's FM-based water heater programs. Right? You have a reference power you want to set. You set a control signal, you turn devices off, and then you pray and hope that it works. There's no feedback. So this could be the water. This could be your HVAC thermostats. You have some power being consumed by the thermostat. You change the set points to +2 degrees. All the devices turn off. And then you have about 2 hours of load reduction before the loads come back on again. Right? That's called a direct load control or demand response. It's kind of classic. More advanced schemes, specifically, if I want to know what the actual power output of my 1,000 HVAC thermostats is, how do I measure that signal? Right? Where does that signal live? That signal lives on 1,000 HVACs across a large geographical region. Like, how do I measure that? And specifically, how do I create an external synchronous estimate of that power output? Right? If you can access synchronous data from all your assets, then you could implement what's called a top-down implementation of a DER coordinator. You can basically broadcast the control signal, you can correct for it with feedback, and you kind of have a classic control system. Another approach in blue, so now you have to ignore the green, look only at the blue. The other approach, the third one, is called bottom-up coordination. So in bottom-up coordination, you don't send a control signal to all the devices at once. Instead, you have the devices ping you for their need for energy, or you have ping you for their, maybe they need energy really badly, maybe they don't need energy at all. And so the devices effectively communicate with the operator, and then the operator or the coordinator basically says yes or no to these incoming requests. What's really cool about bottom-up coordination is that it depends on two-way communications, which isn't too expensive these days. And so two-way communications, it's asynchronous, so it's relatively low communication overhead. But what's really cool is that the DER coordinator, because it says yes or no to each device, can build an internal synchronous estimate of the total power consumed. Right? So if every one of you at different times during this talk would say, hey, I have a question, I can choose whether to accept or reject your question. If I accept your question, I can keep track of how many questions I've answered during this talk. I can have an internal synchronous estimate that's going to be accurate at all times. That's a bottom-up coordination scheme. And so with packetized, we effectively leveraged a bottom-up coordination scheme by being inspired by how the internet works. Our phones, our computers all communicate data across the internet in data packets. Small chunks of data making its way across a complicated network, and then through random access protocols are routed to achieve their final form. And so packetized energy is a bottom-up example. The main thing you need for packetized energy is that each device needs to understand what its need for energy is. Right? For a water heater, it's pretty simple. Cold water, high need for energy. Hot water, no need for energy. In between, various degrees of need for energy. Electric vehicles are a little more complicated. Right? Electric vehicles need two things. How much energy do I need, state of charge, and how many hours are you available for? But if you give me those two pieces of information, I can compute need for energy for electric vehicles, and I can compute it for water heaters. And then I can put that logic on each device, and they communicate with the DR coordinator in exactly the same way. So it homogenizes interactions and makes it super simple to coordinate. Good. So one example of packetized, right? Heating water tends to be this 20, 30-minute heating period called bulky demand. You can cut that bulky demand into small energy packets. And if you defer these packets by a few seconds or minutes, right, you can deliver the same amount of energy over a longer period of time through some kind of stochastic requests, where the mean time to send a packet request is defined by the device's need for energy. Right? And every packet of energy it consumes, its need for energy should go down, assuming you don't shower. But if you shower, then it'll just keep requesting. And so we implemented this for HVAC thermostats, for batteries. We work with Enphase, and we have been working on electric vehicle charging as well, and electric water heaters as well. And so this was basically what packetized energy implemented, this algorithm, and we used it to shape demand. What's really cool is that packetized energy, because of that internal synchronous estimate, at every request coming in, I accept or decline. And because I know which one I accepted, I can keep track of power. And so I can increase the rate at which I accept packets or decrease the rate at which I accept packets. And I can then shape demand. And so you can go from something on the left to something on the right, where you shape demand. And so one way to think of this packet shaping algorithm or method is that we basically solve a super hard scheduling problem, or we approximate it, in real time. Right? We're not going to schedule those packets exactly perfectly because we don't know your shower schedule or your EV charging schedule. But we can, in real time, adapt to whatever changes are necessary to meet the needs of whatever the reference signal is. Cheap energy, low carbon energy, or some kind of supply and demand balance problem. And so we didn't just build this in simulation, right? We didn't just build a few cases of this. We actually implemented at scale. And when RPI saw that we could shape the load in real time, they asked us to go faster, right? Can you provide frequency regulation with packetized energy management? So it gave us 2 years to pursue it. And in 2 years, on December 2021, we delivered frequency regulation using PJM signals with 256 controllable loads. And so it's cute because it's kilowatts on the y-axis, right? So we're not doing megawatts of flexibility, but we proved that we could do it. These are real devices in the field, real-time signals and real data. And what's really cool with PJM signal is that it's pay for performance. So we can measure performance. We can see how well we perform compared to other assets on their system. Right? So their pay performance scheme, they have a score. It's called the performance score, which has 3 parts: accuracy, delay, and precision. And the composite score is what you get paid for. And so we scored 92%. Right? Their natural gas power plants score between 80 and 90%. The only ones that beat us are large utility scale storage, which is pretty awesome. And so we showed that PEM at scale could deliver real-time frequency regulation. And so unfortunately, we only published it in IEEE Spectrum. It wasn't a real journal paper, but oh well. And so we showed it's possible. And so we've been working on kind of this topic of distributed energy management or flexibility for a while. And I think some folks in the room looked at, I think someone said they looked at end use behaviors. And so that's something we've looked at quite a bit. Right? Measuring people's shower schedule, super hard. Measuring their electricity consumption, super easy. can you model or infer shower schedules from electricity consumption? And so we worked on some of those problems. Those are really fun inference problems. And so we have stochastic end use driving a lot of these behaviors, right? When EVs come and go, that's stochastic. And so you can't avoid stochasticity. We have a lot of work on modeling and control of these fleets, these population models. And then when you have these aggregations, they are effectively flexibility with uncertainty. If I want to dispatch a battery that's 1 megawatt, I can get a megawatt, assuming the state of charge is well predicted. But if I have a fleet of 10,000 HVAC systems, what is the state of charge? What is the capacity of my fleet? And so we've been looking at kind of optimizing dispatch, optimizing batteries under uncertainty, or stochastic batteries. And so we have various papers on these topics. But that doesn't answer the question of, great, I can manage devices, but what role does the grid play? And so I love, so peer-to-peer, people have been working on peer-to-peer for a while. Tough sell, because most of these devices reside in tree networks, radial networks. Good luck sharing resources between these two black boxes. That's pretty hard unless it's virtual currency. And so I think there's a lot of opportunity to rethink how we integrate with the network itself. And so distribution systems can no longer be these passive absorbers of energy. So we need to think, how do we take into account network conditions? And so we made this pitch to DOE once, they didn't like it. Telecom business improve performance and resilience by enmeshing themselves. Utility networks are radially operated almost everywhere, except in New York City. And so what if we start enmeshing these systems? Then we have really challenging protection problems to deal with. But if we solve that problem, we can enable much greater resilience and much greater energy sharing. And so we did pitch this to DOE once, and they didn't fund it. But I do think there's role for enmeshing. Anyways, grid is important. We're going to stick with radial networks for now. All right. How am I on time? 10 minutes? We can speed through this. We can do it. All right. So in 2016, DOE did fund this effort, which we didn't know at the time was the total DSO architecture. And the problem was pretty simple. DOE had this goal, 1,000 feeders managing 1 million assets. How do we do so reliably while guaranteeing network limits and managing quality of service and improving various other metrics? And so it's 1 million devices and 1,000 feeders. Right? You can't solve that as one optimization problem. You need a hierarchy of problems. And so we proposed this kind of simple approach. Wide area frequency control, right? The grid that was brought down in Spain and Portugal, frequency is managed through a layer of control architecture. It's managed by control hierarchy. Right? At the system level, you have a bunch of feeders. They're part of a large system. If you zoom into any one of those feeders, you have a three-phase physics. Right? This is the AC physics. This is the residential distribution feeders. These are unbalanced feeders, fairly large models. And if you zoom into any one of those nodes, you have these resources sitting there. And so if we can model the batteries, the equivalent flexibility at each of those nodes, we can kind of aggregate up all that flexibility, and then the utility can dispatch all the flexibility in aggregate. And so we compose this hierarchy of spatial temporal decomposition of the control problem. And so across different time scales and different spatial scales, we've basically developed this market interface, the physics feeder interface, and then the localized real-time controller. And we showed that local flexibility could be approximated locally, fed to the feeders, and then it could dispatch these resources effectively at each node. That flexibility could then be propagated upwards to interact with market signals, whatever the utility is interested in, like peak reduction, wholesale arbitrage. And then the utility can dispatch feeders almost like economic dispatch, with uncertainty as well. And so today I know that Camus and Emulate Energy are basically building both of these building blocks. So looking at feeder dispatch, and Emulate is implementing the real-time controllers. They didn't get it from us. It's just something they're working on. One of the key things that enabled all of this, right, running optimization of large networks and distribution feeders is a really hard problem. If you need to solve this every minute, you can't solve it fast enough with distribution systems. The full networks are too large for computational efficiency. And so what we did was we compressed the full networks into reduced networks. And every node in the reduced network is basically a collection of nodes in the full network. And so the colors, the same colors represent where the super node is aggregated into. And so we showed that this was possible in the project. We showed that the errors resulting, so the physics represented by the reduced networks are very similar to the physics on the full network, which is really cool because then you can significantly speed up computing on this side. We also know that when you select which node is going to be a super node in each cluster, that is could be an optimization problem. So Umid is currently working on this, and I'm working with Sam on this. And so cron reductions, if anyone has worked with cron reduction, when you cron reduce a radial network, you get mesh networks. And so you need to radialize them again to recover your original structure. So Umid has been doing some really cool work on this. We hope to submit that pretty soon. Anyways, so with Nawaf and a bunch of students, so Nawaf was my student at one point, we basically implemented this entire hierarchy. We did it under uncertainty, we did it effectively minute by minute, and we showed that it was possible. Right? We showed that the grid market layer, right, the market incentive signals, could be tracked with these feeders. Right? The feeders could provide the necessary flexibility at the right times and place. We showed that the reliability of the network was maintained because voltages never exited their ANSI limits. And so we showed that despite this being a pretty complicated system across many feeders, many devices, lots of opportunities for making the wrong turn, we showed that we'd make the right choices robustly. And so to go to DOE, when you can show something works, right, it kind of works, but DOE loves to say the proposed framework is technologically viable, which was pretty awesome. It was a cool project. And so what happened a year ago, somebody found our technical report from DOE. So New York State, the Department of Public Service found our report, contacted me and said, hey, can we implement this in our actual system? And so I've now taken on an additional role, so another hat, to basically help New York realize their grid of the future vision with phase 4, which is going to end in a large-scale demonstration of effectively different types of control architectures, with total DSO being one of the things we're looking at, and another approach being a different one. And so it's always cool to see that some of the works we do ends up on DOE, on OSTI, and then somebody looks at it, and somebody contacts us. So it's pretty cool. I'm pretty happy with this. This has a chance to make, I think, a positive impact. And I'm just doing the work. I'm not paying for it. So no startup company for this. Anyways, so DOE is great at showing that things can work, but in science, we like to go beyond just making it work. I try to understand when it doesn't work, right? How much flexibility do I have? Can I find, instead of just showing I can track certain market signals at certain times, can I quantify the set of signals that can be tracked? Like what's not possible with this system? And to answer that question, we need to think about a different architecture, right? What signals are not trackable, right? What can flexibility not do? What are the limits of the feeders? Right? How do I define the limits of the feeders? And so for that, we again get inspiration from the internet. So when I was in Denmark, I bought 1,000 megabit per second internet. Megabit per second, it's like power, right? Megabytes per second, that's a power resource, that's a power limit. I bought a portion of the bandwidth of the network. Why can't we think of distribution feeders as having some portion of capacity that I can procure, just like I do with the internet? So what if instead of procuring internet and dealing with bottlenecks, what if flexible resource can access markets, and then we can somehow help utilities find ways in which to manage these dynamic hosting capacity challenges? And so what if utilities could send some kind of signal to aggregators that says, hey, at each of these nodes, these are the power injection limits you have. And this is the dynamic hosting capacity, similar to an operating envelope. And if you give these limits and the aggregators enforce them, then they have free play to do whatever they want with that flexibility. Right? We basically have pre-filtered their flexibility limits. And then they can pursue whatever market signal they want, and the utility knows that the grid is going to be safe and reliable. And so we've been working on this topic for 5-6 years now. Jeez. Okay, yep. Started at CDC in 2016, or 19. And we've been working on it ever since. And just recently, so this summer we'll be heading to Italy and share some of the work on kind of when you allocate proportions of a network, right? How do I know that Aaron's proportion is not much smaller than mine all the time, right? What if Vikram's proportion is much bigger than everyone else's? That's unfair. And if we're dealing with market access, there has to be some kind of fairness measure. So we found some really clever ways in which to incorporate fairness into these hosting capacity limits and studied how it impacts solar PV curtailment schemes. So one caveat to all of the science here, simple networks, single phase, radial, no more three phase. That was earlier. At the core of this, some science is good to include. At the core of this, it's really so a lot of people work on optimization. We always love finding the optimal solution, right? But generally, optimization problems are non-convex, which means they're really hard to solve. They're NP hard. And so a lot of folks have done the red trick, right? You convex relaxations, and so you can find solutions that aren't real, right? They might be optimal, but they're not real. For power systems, we need solutions that are real and reliable. And so what we've been focusing on a lot is what's called convex restrictions, right? So instead of pursuing optimality and falling out of reliability, we've been sacrificing optimality and ensuring reliability. And so there are lots of really cool ways to do this. I'm happy to talk through this at dinner. I'm sure that'll be really exciting for everyone. But what's really cool is this. Imagine that you can create two different universes, one that over-approximates everything and one that under-approximates everything. As long as those two universes are within their limits, then I know that reality is within the limits. Right? And so I can kind of squeeze reality between two universes, and as long as these universes are simple and easy to compute, I can guarantee that the reality we live in is safe and reliable. And so it's a little bit hard to see here, but that white space between the two lines, that's reality. And I can squeeze it between two convex shapes, and a fine line and a second-order cone. So that orange space is the positive reality, the green line is the negative reality, and the actual reality is in white. In between is the blue line. You can barely see it. What's really cool is that that allows us to kind of build these convex restrictions that have a certain shape. Right? They're effectively corner points. Instead of ellipsoids, they're kind of corner points. And they give us the upper and lower bounds on injections. And so let me give you one use case. PV hosting capacity. PV hosting capacity generally is super conservative. Utilities take the lowest demand of the year and the highest solar output of the year. So that's nighttime load and noon solar. And then they say, oh, based on these two conditions, most solar you can put on here is whatever it is. And once you hit that limit, the feeder goes red, right? And red means stop. No more solar PV on that feeder. And so the question is, can we do more than that? Right? So what we did was we took a network, we applied our convex restrictions to it to develop at each node a range of allowable, admissible injections, or specifically solar PV injections. And then we said, okay, conventional static hosting capacity is red, we can put that much solar on the feeder, on that one node, like node 25. So every node that's orange has solar PV. What if I put this much solar on the network? Okay. Now I'm going to violate safety limits. Then I apply my hosting capacity limit. So that green line, that's my P plus. Oops. Right, so that's the dynamic hosting capacity. So that takes into account real-time demand. And so what happens? Any generation above green must be curtailed, right? Because it's unsafe. And so I curtail that. But what is the benefit? Right? All that green is new energy that I couldn't produce before. So I'm producing significantly more energy, even if I curtail some. And so what we showed, and this isn't our studies going back like 2016 in Germany, showing similar results. And I think if you know Tyler Norris, he basically has done the same thing for data centers. And so what we showed is that capacity increase. We can add 50% more solar PV capacity on this feeder if we only have a 5% annual curtailment. Right? Snow losses in Vermont is like 12 to 15%. Right? 5% curtailment allows 50% more renewables, which is significant energy benefit. And then we did this crazy things, which I'm not sure the NSF will fund anymore. We said, if that extra energy is clean, I'm offsetting 30 fossil fuel generation. And if I had a price on carbon, I can show the benefit, the social benefit of this additional energy. And so we can see here that you can actually pay this program where you curtail people's solar, you can actually pay for it with the socialized benefits of carbon, assuming the carbon price is more than 50, which is also an open question. So what's really cool is that this idea of curtailing people's solar, no one would like that, but you can get paid and be made whole and more under pretty reasonable pricing assumptions. And so this idea, I think it's pretty cool. I think it's fun. So we reduce CO2 emissions, provide social benefit. We haven't quite figured out who should pay this, but maybe somebody can tell me that. And then we did get a DOE project funded under Biden. We're still waiting on this one. This is basically implementing this in the field with a utility partner. All right. Good. Finishing up. I have 1 minute. So there are devices, there's flexibility, there are grid operations, or reliability. Right? The grid and the DERs, we can't deny that they're physically coupled. What's currently lacking is the correct data sharing. We don't know what signals to send between utilities and DER operators. I've tried to make the point that these hosting capacities could be really meaningful and pretty easy to compute limits that the grid operators and DER coordinators can share today, similar to operating envelopes what's done in Australia also today. But what I do think we need to think about, and this is where the science is fun, if you want to just do basic dispatch, Tesla has conquered the auto bidder, right? You can dispatch batteries, it's pretty easy. Right? You can dispatch it against market signals, it's pretty easy. Frequency regulation, we can do that. But if you start to impose any grid reliability requirements or any comfort requirements on thermostats, it gets a little bit more tricky. And so I think there's a lot of opportunity to pursue hard problems in the upper right corner, right? To really scale virtual power plants and to do it in a reliable fashion and to do it in an affordable way. And so I think there's lots of opportunities for synergizing data, sensors, computing, control, and optimization. Pretty small words. How many PhDs are in this? I don't know. Oh, a lot of PhDs. Anyways, I don't have time for the last bit. Oh, do I have time? A minute? No, I don't think I have time. This is a really cool problem. We have time. All right. So we talked about inner approximations, how we can restrict the space of options of dispatch solutions. And so if you work with battery dispatch, if anyone has ever optimized batteries, what you often see is a model like this on the left. It's a nonlinear model because you have this non-convex complementarity condition. Like UC times UD equals 0 is a nonlinear complementarity condition. It makes the problem NP hard, which means that your dispatch must lie on this black thick line on the Tesla Powerwall. You either have to charge or discharge. You can't do both. And so a lot of the literature basically ignores it, which means now your dispatch can lie anywhere in that red rectangle. A few smart people have been truncating that rectangle without any loss, and now you have a smaller search space. What we did recently, this is a couple of years ago now, feels like recent. What we did recently was we basically used the same idea of inner approximation. So we said, what if I can create a state of charge that is guaranteed to always be above the actual state of charge? And what if I create another state of charge, x lower bar, that's always below the state of charge? And I have two states of charge that are fake, but I know that the reality is in between. Then I can drop that complementarity constraint altogether, and I have a linear optimization problem. That solves in milliseconds with guarantees on optimality and guarantees on realizability. I can implement that battery trajectory. I can do it. So when we published the paper, like a year ago, I heard from Form and Shell that they basically have taken this work and started to implement it on their planning tools because it gives you guaranteed dispatchability. The Form one is a little bit tricky. There's one downside to this, that the conservativeness grows over time. So Form has long duration energy storage, so it doesn't really make sense to me why they would do this, but they told me they were looking at it. Anyway, so you constrain basically the lower bound and the upper bound. And then you can show that these trajectories, blue and green, always contain reality, which means if I can dispatch my linear model, I can implement it on the nonlinear model. So you take an NP hard problem and you make it NP easy. So it's pretty cool. If it's this feasible, it's also nonlinear feasible. And so we recently extended this, and I talked to some of you guys today about this. So this is some nice work by Nawaf, but this was Mazen has been extending. So Mazen has been extending this. He'll be graduating in a year or so. He's very good. All right. So I apologize for not giving you 10 minutes of questions, but maybe that was my strategy in the end.